Let's wrap up our study of trigonometric equations by learning about trigonometric equations of quadratic type. Recall from college algebra that a quadratic equation takes the form ax squared plus bx plus c equals 0. That is, it is a degree 2 equations. Now, an equation in quadratic form can be written au squared plus bu plus c equals 0. This looks just like the first equation that we wrote, but instead of an x, we have a u. What we want to recognize here is that u represents some sort of function of x, and that could include a trigonometric function. To recognize quadratic form, we want to notice that the variable part of our middle term is half the degree of the variable part of our first term. Recall from college algebra that quadratic equations can be solved using 4 different methods. The first one, what we're focusing on in this video, is the square root property. In addition, we can solve quadratic equations by factoring. That's a very fast and efficient method. Number 3, we can solve quadratic equations by completing the square. We're not going to use this to solve trigonometric equations of quadratic type, but I do want to remind you that that method is what is used to develop the last method, which is quadratic formula. So in 4.4, we'll look at using the square root property, factoring, and the quadratic formula to solve trigonometric equations of quadratic type. Let's begin by reviewing the square root property from algebra. In example 1, we have 2 degree 2 quadratic equations. We're going to solve these with the square root property. Recall that to do that, we need to isolate the x squared term. So in equation A, we can subtract 3 from both sides and then divide both sides by 2. Now here's where this method gets its name. We're going to apply the square root to both sides, recognizing that we're going to get one positive and one negative root. Thus, our degree 2 quadratic equation has 2 possible solutions. These are -4 and +4. We can also solve example B using the square root property if we first isolate the squared part. We can do this simply by dividing both sides by 3. And then we can take the square root of both sides. Remember, when you apply the square root to both sides, you get one positive and one negative root. On the left side, the square root and the square cancel out, leaving behind just the base, x minus 1. And on the right, we have 2 possible values, plus or minus 3. Now, unlike our previous example, at this point, we still have a little work to do to isolate x. We're going to add 1 to both sides. Now, to make this easy to read, I like to put the 1 in front of that plus or minus sign. So notice we do have 2 distinct solutions here. One is 1 minus 3. The other one is 1 plus 3. So our 2 solutions then would be -2 and 4. Remember, degree 2 equations or quadratic equations have 2 solutions. Both of these would balance the original equation if I were to substitute them in for x. Now let's take this same algebraic strategy and apply it to a trigonometric equation. In example 2, we're going to find all solutions to each equation in the interval 0 to 2 pi. We're working on a closed interval, 1 rotation around the unit circle, or I suppose I should say a half-open interval, right? And the interval also indicates that we should be working in radians. So on example A, we have cosine squared of x equals 3/4. This is a trigonometric equation, but because of the square, we could say it's of quadratic type. Notice the squared part is by itself on the left. So because the quadratic term has been isolated, we can go ahead and apply the square root to both sides, recognizing we're going to get one positive and one negative root. On the left side, the square root of cosine squared of x is cosine of x. And on the right side, we can split up that radical over the numerator and the denominator. You can see that this leads us to cosine of x equals plus or minus square root of 3 over 2. Let's find all of the angles on the unit circle. with a cosine value of plus or minus square root of 3 over 2. So we're looking for an angle whose x-coordinate on the unit circle is plus or minus square root of 3 over 2. In radians, we'll end up with angle pi over 6 or 5 pi over 6. In addition, 7 pi over 6 and 11 pi over 6. Because we're not dealing with a multiple angle equation here, it's not necessary to first express the complete solution because we have clearly found all solutions in one rotation around the unit circle. So I'm going to write them in a set in order from smallest to largest. This can be checked either by substituting each individual angle into the original equation or setting the equation equal to 0, graphing it, and observing that there are, in fact, 4 x-intercepts. So we've solved our first trigonometric equation of quadratic type, and the technique we used there was the square root property, that is, taking the square root of both sides. Let's try that on example B. This time we have a tangent equation. Now, before we can apply the square root to both sides, the squared part has to be isolated. Remember on example B up here, the first thing we did was isolate the quadratic factor. We're going to do the same thing here. So let's add 1 to both sides, and then let's divide both sides by 3. This isolates the quadratic term. Now, we can apply the square root to both sides, remembering that we're going to get one positive and one negative root on the right side. The square root of tangent squared is tangent of x, and I'm going to distribute the radical to the top and the bottom of this fraction. So tangent of x is equal to plus or minus 1 over the square root of 3. Recalling all the way back from chapter 1 that tangent is the y-coordinate divided by the x-coordinate, I'm going to find all of the angles on the unit circle with a y-coordinate of 1/2 and an x-coordinate of square root of 3 over 2. Hopefully you recognize the reference angle there would be 30 degrees, or in radians, that's pi over 6. We're looking at positive or negative 1 over the square root of 3. So interestingly enough, this equation has the exact same solutions as our previous equation. 5 pi over 6, 7 pi over 6, 11 pi over 6. If we were to graph the left side of this equation and observe the x-intercepts of that function between 0 and pi, we could see that there are 4 x-intercepts. Listing our solutions from least to greatest, we have the solution set in one rotation around the unit circle. So once again, this last part is very similar to the technique we've been practicing. The new part is the fact that we are applying the square root property to first solve for the trig function and then carry on from there. Now, because both of these equations have the same solution, it might be interesting to see how this plays out on a graph. First of all, I'm going to make sure that I'm in radian mode, and then I'm going to pop over to y equals and enter my first equation. The first equation was cosine squared of x. We can type that in as cosine of x and then hit our square button to square the entire function. Minus 3/4. I'm moving the 3/4 to the left so that it's equal to 0. The x minimum should be 0, x maximum should be 2 pi, and let's set our x scale to be multiples of pi over 6 since our answers were multiples of pi over 6. So here's the graph of the left side of the equation, of course set equal to 0. Notice we have 4 distinct solutions. Now I'm also going to graph the second equation here for y2. We'll type that in as 3 tangent of x squared minus 1. And let's observe that this graph shares the exact same x-intercepts, pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So we verified both equations in one graph. That's pretty efficient.